Hello, this is Jeff Hamrick at Rhodes College, and I'm going to develop a couple of screencasts here in which we construct the confidence interval for a true population mean using the trial and error method that we recently deployed to build a confidence interval for a true population proportion. Our method is going to be the same. To kick off this method, let's remember our philosophy for hypothesis testing a single mean. I'm going to create a simulated set of body temperatures. Let me drop down this empty collection and call it simulated temperatures. Okay, and I'm going to create a synthetic group of 130 test subjects. Let me add 130 cases here. And I'm going to simulate their body temperatures. So I'm going to call this simulated temperature. And my philosophy is going to be that I'm going to choose the mean of these simulated body temperatures, but I'm going to have the simulated body temperatures have the same sample standard deviation as the original set of body temperatures from the original set of data for this study. So recall that when we were conducting the hypothesis test, we right-clicked on this attribute column, edited a formula, and the formula that we wanted was random normal to test the null hypothesis h sub 0 mu equals 98.6. We entered 98.6 here for the mean, and we copied the sample standard deviation from the set of body temperatures from the original study. And in this case, that was 0.733183. Okay? Fathom will simulate 130 instances of body temperatures with my null hypothesized mean of 98.6 degrees, and it will match the standard deviation of these simulations to 0.733183. Okay, so I'm going to define a measure on this simulated set of data. That measure is obviously going to be the mean. So I'm going to call this mean of temperatures. And it's the mean of the simulated temperatures. Okay. And in this particular case, we get 98.5688. And recall the basic strategy for hypothesis testing here. I'm going to collect measures repeatedly, not just 5, but after I shut off the animation here, okay, replace existing cases and recollect measures when the source changes. Remember, that's important when we're doing confidence interval construction by our trial and error method. I'm going to collect a relatively large number of measures, like maybe 1,500. Okay? So I collect more measures. It doesn't take terribly long here. I'll table off from this collection of measures and then create a picture of the randomization distribution. Okay? And recall that what we basically observed was that our data, which has a sample mean body temperature of 98.2492 degrees, lies so far off to the left here that our empirical p-value was 0, and we rejected the null hypothesis that the true mean body temperature is 98.6 degrees. The question now arises, though, if it's not 98.6 degrees, what is it? And so to determine what that might be, I'm going to go on ahead and plot, even though it doesn't show up right now, the body temperature of our original set of data right here. It's off here to the left. It'll eventually show up as we move this distribution around by changing the simulation formula. And I'm going to go on ahead and move the simulation formula to the left a bit. So let me right-click on this. And if it's not 98.6 degrees, maybe plausibly it's 98.4 degrees. Okay? So I'll press OK here. Okay, and there's my blue line. And it appears to be sweeping out a relatively small proportion of the dots. That is, a relative proportion of the dots are to the left of this blue line. I can't really tell exactly what proportion that is, so we need to go on ahead and compute the empirical p-value. So I'm going to open up this measures box and define a measure on the set of measures. And I'll call that, as usual, empirical p-value. The formula for that will be the count of the mean of temperatures that are less than or equal to 98.2492 degrees divided by the count of the mean of temperatures. It's 0.006 in this case. I'm going to wrap up this screencast. In part 2, we'll talk about how we interpret this and begin to use this empirical p-value to help us construct our empirical confidence interval.